have spent more than the time allotted for questions. So please go ahead with the second part, Marco.
Yeah, the second, don't worry, the second part is not going to be the same length of the first part. It's much, much shorter, just 2 slides. So, uh, so in the second part, I wanted to connect this with Schubert, whatever that means. And the connection is the following. We have this corollary, and the corollary of our theorem is that if n is odd, then the Fukaya category of the Grossmanian 2n is generated by a Catalan number of tori, and I wrote which number here. So let me just in one slide try to convey what's the Fukaya category, and then in the next slide I'll say why this is I call this open string Schubert calculus, a kind of open string Schubert calculus result. So just in a nutshell, there is a family of A infinity categories you can attach to a broad class of symplectic manifolds, like a Fano manifold in this case. And they're denoted by F lambda. So the objects of each such category are Lagrangians that satisfy a technical condition. So I'm not going to explain it here, but it's something related to lambda. Think of it this way. And then whenever you have two Lagrangians, you can, because Lagrangians in a symplectic manifold are half-dimensional, they will intersect in finitely many points. And so you can take those as a basis for a vector space over the coefficient ring. I'm denoting coefficients for these categories lambda. And I don't want to explain what this is. So in a Fukaya category, just like in any category, you have some composition law. And that means that if you have, in this case, three Lagrangians that form a triple of Lagrangians that intersect, let's say L0 and L1, in my example, intersect here, L1 and L2 intersect here, L2 and L0 intersect here, then you remember this point of intersections, they really give you morphisms between L0 and L1 and L1 and L2. So there should be a way to compose them. And the way in the Fukaya category is to look at intersections between L0 and L2, and count holomorphic triangles whose corners connect the intersection points. So this gives you a composition law, but unlike a normal category, this composition is not associative. It's only associative up to higher composition maps that are defined counting polygons whose number of edges is greater than 3. But there are two basic things you should know about Fukaya categories. The first is that so this parameter that enters the definition makes them 0 unless the parameter is an eigenvalue of multiplication by the first term class. This was a result by Roux in 2007. The second is that they categorify quantum cohomology in the following sense, that if you take one of these eigenvalues to each A infinity, just abstract infinity category, in homological algebra, there is a way to cook out a ring out of it by taking the so-called Auchy cohomology. If you do that to the Fukaya category with parameter lambda, you recover a certain subring in the quantum cohomology, which is the generalized eigenspace for this eigenvalue lambda of this operator. So this slide is just meant to convey the idea that there's a gadget, the Fukaya category, that generalizes in a way quantum cohomology, and the way is precisely this one. And the reason why, I guess, historically people have been interested in this, one of the main reasons, in my opinion, is the fact that quantum cohomology is notoriously difficult to study so it's difficult to study its factoriality. There is no clear factoriality for quantum cohomology, unlike with ordinary cohomology. Whereas instead, these Fukaya categories afford a factorial nature. So it's known that certain things called Lagrangian correspondences, which are analogs of morphisms for symplectic manifolds. They induce functors between Fukaya categories. So that's a big reason why people, endure the pain of studying these more complicated invariants instead of just studying quantum cohomology. Okay, so, and the conjecture that I guess I've been interested in the past few years is the following: a conjecture that the Fukaya category of any homogeneous space, so all Grassmannians, but any really partial effect varieties as well, and not just type A stuff in any type. Any G mod P has Fukaya category generated by Lagrangian tori. Okay, and let me try to convey why I think this is an interesting statement. So they're these Fukaya categories are new enough that people have not computed them in a lot of cases. In fact, in the compact targets, the toric Fano case is essentially one of the few we understand. I'm not going to give you a full, I guess, history of what's known, but let's say the toric Fano is one of the basic things we know. And one, the case of GMOP is a natural testing ground for calculations of this gadget. And it has a connection, historical connection with Schubert calculus that, started. I guess I should not be explaining this here, but you know this much better than me. But the cohomology of G mod P was, computed starting as a motivation from problems in Schubert calculus, and then the quantum cohomology has been studied as a way to extend those results. And so I think of this computation of the Fukaya category G mod P as some sort of new iteration of this story that returns in mathematics. So the statement that this is generated by tori is a reasonable statement because it's known that the quantum cohomology of G mod P at Q equal 1, let's say, can be presented uniformly in all types as the ring of regular functions on the critical locus of a potential on a so-called mirror affine variety V. This is a result by Peterson and Rich. And this potential, so I'm drawing the mirror affine variety here, and the critical locus of the potential like here, like many critical points here. And so the mirror partner to the Fukaya category is expected to be the category of singularities of the critical locus, which is supported in this case as skyscraper shifts at these critical points. And those are known to be generated by things that look homologically like Lagrangian tori on the other side. So we have a strong evidence that if we believe that this is a correct mirror for G mod P, then we have strong evidence that the Fukaya category G mod P should be generated by tori. And as the general strategy I'm trying to follow to obtain this kind of results of generation by the Fukaya category is to use cluster algebras and this cluster structure to look now at how these critical points are distributed across the different torus charts. And what happens is that we know now in full generality that for any G mod P, the mirror has a cluster structure. So this was established recently by two groups of people led by, I guess, I'm just listing the first authors. Each of them is a paper with many authors. So Casals and collaborators, Galashin and collaborators. And it's also known from the work by Gross, Sakin, and Konsevich, and their students, Cheng, student of Gross, and Maji, student of Kiel, and collaborators. So it's known that from the data of each of these charts, it's possible to construct a degeneration of G mod P to a singular toric variety that I'm denoting here as fibering over its moment polyton. And so there is a way to really construct certain Lagrangian tori in G mod P that sort of correspond one-to-one to these charts in this mirror affine algebraic variety. And so the idea is that each critical point that falls in a given chart should correspond to an object supported on the geometric Lagrangian torus on the other side. And in particular, more precisely, should correspond to a local system that twists the endomorphism algebra of that object to make it a generator. So what's the connection with the theorem? I explain, and that will be the last thing I say. The point is that, as I stressed in my talk, in general, a cluster structure only gives you cover up to a locus that I call D. So this is what I call D in my talk. And unfortunately, the critical points of this potential can't possibly fall inside this critical locus. So when that happens, there's no clear geometric construction of a corresponding object in G mod P, and there is no clear evidence that the Fukaya category in that case will be generated by at least this particular class of Lagrangian tori. And so our theorem says that it gives us a way to say that sometimes this D is empty. In that case, that difficulty in this general outline disappears, and we're able to obtain generation statements for the Fukaya category and verify Kontsevich homological mirror symmetry. And even in the cases where our theorem does not say that this is empty, at least it gives a way to interpret this torus as living in charts of lower dimension, as I was mentioning to answer Andre's question. And so we're still hopeful that it will lead some other results in those cases as well. Okay, thank you.
Thanks very much to Marco for a very nice talk.